So we've been talking about the normal stresses that result in a beam as a result of bending. But there's also shear stresses that occur as a result of bending. And so we need to give some time to look at shear stresses in a beam and figure out what that might mean. So, I bring your attention back to when we looked at those in-plane shear stresses very specifically, and our shaft in torsion, our wooden shaft in torsion, how because of the in-plane nature of those shear stresses, when we twisted that shaft, we ended up introducing a longitudinal split between the fibers because there's this weak plane between the fibers. Even though the shear stresses that we were thinking that were in our mind were occurring in this axis because of the in-plane nature of them, the failure actually occurred in the longitudinal direction. And so I want you to think of that as we look at these beams. So we're going to start a little conceptually, and we're going to go back to our 2x6s that we talked about when we were looking at geometric properties. Only in this case we have a stack of them, and a stack of 3 2x6s. And we've got to get across our ditch, and we knew that we didn't trust ourselves to balance on the end of it, so we couldn't stand it up on it. So we're just going to stack 3 2x6s across the ditch so that we can walk across it and get across without getting our feet wet. And what we note when we step on them is they bend, as we would expect. But when they bend, we notice that the ends don't line up anymore. So when we look at the ends, they don't line up anymore because they're slipping one relative to the other. So where they're touching, the friction that is connecting them isn't enough to stop them from slipping one relative to the other. So they're all behaving independently. They're not behaving together as one composite section. And this is because of those longitudinal shear stresses that we need to resist. If the friction was strong enough that it was able to overcome those longitudinal stresses, then these pile of 3 2x6s would start to behave compositely and act like a single beam rather than 3 little beams stacked on top of each other. And so the way to overcome that is we're going to have to find a way to connect these 2x6s so that they're all behaving dependently, and we do that by bonding them. So we can use glue, nails, staples, welds. Well, it doesn't really matter, depends on our cross-section. But so we have to make sure that the entire cross-section is not going to slip relative to each other. And that's really a good indicator of how these shear stresses exist inside our beam and how we're going to have to design our beam to resist them. So if we do bond them together, we get this nice composite behavior. We note that our plane sections remain plane. We have a single beam, but to do that, we need to achieve sufficient resistance to those cross sections, nails, glues, welds. It doesn't really matter what it is. Independently, how much less is it able to resist? Well, think of that parallel axis theorem and our moment of inertia. If they're behaving independently, there is no parallel axis theorem. All you have is its own moment of inertia about its own axis, 3 of them stacked up on top of each other. Whereas if we can bring them all together, the top one and the bottom one are going to have an 80 squared term in addition to their own moment of inertia. So that's why the composite beam is so much stronger than just independent beams. So shear stress is really important in beams. We're going to have to look at them, and that's what this section is all about. So we're back to our little can here. A slice of our beam. We've been here before. It's dx. We have our axes shown, and let's get some forces on it. Now, because we're looking at shear stresses, in this case, we're only really going to be looking at horizontal equilibrium or equilibrium in the x direction in this case. And so we put on our moments. So on the left face, if you will, you have a moment m, and then you have some other moment m plus an increment dm on the other side. And what we want to do is then reflect those in their stress distribution. So remember, everything we've learned about our normal stress distributions. So we have our neutral surface, we put sigmas on it. So you're going to have going to sigma on the left side, you're going to have it going to sigma prime, which should be higher than sigma on the right hand side, because m plus dm is implied as larger than m. And so looking at it from the side, or side view, you see your m, and on your left side, your m plus dm, and the stress distributions, as we often draw them. We don't normally draw in 3 dimensions, a little bit awkward. We draw them in 2 dimensions. And so we see them here varying linearly from 0 at the neutral axis up to the maximum at the extreme fibers. In this case, sigma prime on the right-hand side being slightly larger than sigma on the left-hand side. So these stress distributions, of course, they are, or their integral is what creates the internal moments, the m and the m plus dm. And so we can represent those moments as force couples, df double prime and df prime, compression and tension on either side. And that concept of those forces, those longitudinal forces resulting from those normal stresses, creating that moment, is what's going to allow us to look at equilibrium. So what we want to do is we want to just take a slice of this beam. Remember, we're looking at that interface between different sections of the beam and making sure it's not sliding relative to each other. So we want to take a slice of our beam, and so we're going to go up a height y prime, and we're going to look at the section which right now is shown as transparent, everything above y prime, and we're going to isolate it and consider it. So let's pop to the next slide where we can see it more clearly, where we get rid of the rest of the beam cross section. So a couple things to note. So we show the area of this section as a prime. It's got a thickness at the point of interface of t, right? Width t or thickness t. Of course, the thickness of our slice is dx. We still have sigma on the left side, sigma prime on the right side. And the height to the centroid of this cross-section from the neutral axis of the original cross-section is denoted as y bar prime. So now, we're showing our m and our m plus dm with our stress distributions of the component that is remaining here. And we recognize, because sigma prime is larger than sigma, that the only way we're going to get longitudinal equilibrium is if there is some force contributing to this that we're not seeing right now. And that force has to be at the interface of the rest of the beam contributing to that section of the beam, and we show that as a shear stress tau. So let's use our formula for equilibrium. So sum of the forces in the x direction, set it equal to 0, and let's start looking at what we have. So we have the integral over the area of the section A prime is equal to, on the right hand side, sigma prime times our dA prime. And then on the left-hand side, we have the integral over the area of sigma times dA prime. And so that then needs to have a negative of the shear stress, tau, multiplied by the area over which it acts, which, if we go to the left-hand diagram, we see is dx as the thickness of our slice times the width at the interface, which we said was equal to t. And we set that equal to 0. Now let's substitute. So we'll take our flexure formula from the last lecture. So sigma equals my over I. And we're going to substitute in here. So keep in mind that we have sigma prime. So we need to substitute in m plus dm over I multiplied by y in that term. And then in the next term we have sigma. So we're just going to substitute in m over I. times y for that term. And then we're able to simplify that slightly. We'll bring out of the integral the dm and the I, leave in the y dA prime, which is equal to tau times t dx. But let's bring that t and the dx over as well, so we can isolate on the shear stress. And we get the shear stress is equal to this term shown here. But we can start to pull that apart a little bit. So what do we have? We have 1 over it, not much to do with that. So dm by dx, start thinking back to the relationship component of our shear force bending moment diagram discussion, where we had relationships between shear force and bending moment. And so the dm by dx means something to us. That's the slope of the bending moment diagram. And if you think back to that lecture, you will recognize that the slope of the bending moment diagram is equal to the magnitude of the shear force. So we can substitute in v for dm by dx, and the integral over the area of y dA was a geometric property q. So there's our q, there's our v. We substitute in q and v for those, and we end up with our formula for shear stresses due to bending. Tau is equal to vq divided by it, where v is our shear force, q is our first moment of area at the point of interface where we're interested in, divided by our moment of inertia and the thickness of the cross-section at the point of investigation. So we've looked at the distribution of Q. So it's just one step further to start to think about the distribution of our shear stresses, which is perhaps to us most important. So we'll set up our rectangular cross-section that we had before. And again, this is just a recap from the cross-sectional lecture. So we have Q equal to the integral from y1 to h over 2 by dy, and that's for that area. And we plotted it out, and this was done before. So Q is equal to this distribution, where it's a maximum at the neutral axis of bh squared over 8 and 0 at the extreme fibers. And so if we take our formula from the previous slide, so tau equals vq over it, and we substitute in q for that, we come up with another formula in terms of v, b, h, and y that we can use to plot tau. And tau, as you would expect, looks very similar to q, slightly different values, but it is a maximum at the neutral axis, and it goes to 0 at the extreme fibers. The actual values here are less important. They'll be more important when we're actually calculating them out. But it becomes really, really important, because when you're considering where I want to calculate my shear stress, you typically want to calculate it where it is a maximum. So you have to figure out where in the beam the shear forces are likely to be a maximum, and then you have to figure out where in the cross-section the shear stresses are going to be a maximum, and that answer is in this diagram, which tells you that it's going to be a maximum at the neutral axis. You may also be interested in it at other points, particularly if you have to design a connection, for example, a weld between a flange and a web, or something like that. So off to do our problem. So this beam we've been using before. So this is the one where we did our cross-sectional properties. We calculated our y-bar, we calculated our moment of inertia, we calculated our q at the neutral axis, and those values are given here as your starting point. We also have our reactions for it, as well as our shear force and bending moment diagram, so we get all of that in here. And what this is saying is determine the resultant maximum shear stress. So there's kind of a two-step problem in deciding where that maximum is going to occur. And so you know it has to occur for the most part, where V is a maximum. We see, or we go to our shear force diagram to figure out where V is a maximum. We see that it's a maximum somewhere between the supported A on the left-hand side and the point load being applied. And so anywhere in there, it's going to be a maximum. But then, as we talked about in the last slide, it also needs to be a maximum within the cross-section, and that's going to happen at the neutral axis. And so you have to understand those fundamental behaviors and relationships in order to even identify where you need to do your calculation. And so this one says, go and find the maximum shear stresses. If you didn't understand that, you wouldn't know where to look. So the link is up here. I invite you to go to the link to walk through this problem longhand, see it all worked out line by line. Shear stresses due to bending. I think probably because Q varies in the neutral within the cross section tends to be a little bit confusing for students. So take some time on it. Have a good look at it. We'll talk about it if there's any questions. So shear stresses, we see them all the time in beams because we do built-up beams. So we know that they are occurring within the beam itself, not usually a major issue, but we see them in built-up beams. We see them in I-beams, plate girder beams. Obviously, a laminated beam there would have a glue line or some sort of a line between each of the different sections. You have nails in the box beam. All of these have to be designed so that they behave compositely. Even the one on the right-hand side, that's intended to be two C-channels, and then it's got shear studs sticking up for the concrete flange, and the concrete flange is cast around the shear studs. But if it wasn't for those shear studs, it wouldn't transfer those shear stresses between the two sections. It wouldn't behave compositely, and you wouldn't get the resistance that you need to get to be efficient and effective as an engineer. So designing these members is achieved in two stages. Typically, we design the whole beam as a unit. We assume it's composite and we go about it. But then we have to go about designing the connection to ensure that it does behave that way and it's not overwhelmed by the shear stresses between the various components. So this is just a diagram, shows a composite section, this one out of timber, one that you might have. We have seen this equation before, and what we want to do is we want to identify something called shear flow, which is the force per unit length required to resist those longitudinal shear forces. And then we can design the connection to make sure that we have sufficient capacity to resist it. So Q is shear flow, force per unit length. We know by definition that would be dF by dx. So if we take our formula, which we already had, we divide it through by dx, we get dm by dx all multiplied by q over I, because that integral y dA is q, all coming together. And if I were to simplify that, remember your dm by dx, we talked about that on the previous slide. That is that relationship from the shear force bending moment diagrams we talked about, where the slope of the bending moment, or the change in the bending moment, is equal to the shear force. And so we can replace dm by dx with v, and we get shear flow, force per unit length, is equal to our shear force multiplied by our q, all divided by I. So now when you're looking at shear flow, you have a V that's fairly obvious. You have the I fairly obvious. Depending on the complexity of the cross-section, you have to identify the component which you're going to isolate in order to calculate Q. Remember, when we calculate Q, we sort of make a cut it, and then we throw away everything else, one side or the other of the cut. And so being able to identify that cut, it becomes really important, particularly in a complex beam. Now, clearly those cuts, or those cut planes, are going to occur where we're designing our connections. And so here we see just a few examples of what you might do. So in the The one shown there, you're going to have to cut it where the nails are, so you're going to throw everything away other than the darkened side of the timber and calculate Q for that, and that will give you your shear flow, and then you're able to design your nails. Here we would probably throw away the webs, just keep the flange and go from there. And here it gets even a little bit more complicated again. I would keep the flange, throw everything else away, use that for my Q, and that would give me the shear flow for the three faces that I would then have to divide up between the three faces. So let's get on and do an example. So we have an inverted T, similar to some of the examples that we've been looking at before. But in this case, what we want to do is we want to calculate the number of nails required to hold the bottom flange to the web and to transfer that shear force at that interface. And so it's a great little example. It's done up, follow the link. It's done up slow speed. I think you will get a lot out of it. And we'll talk about it later.